I'm gonna do some math. Got my calculator in my pocket. I'm doing some logarithms. This will be so awesome. There's your song for those of you that heard my geometry kids get songs and you guys don't. So today we're going to talk about exponential and logarithmic functions, specifically logarithmic functions and their graphs. So yesterday we did exponential, today we're doing logarithmic. So what are logarithms? This might be a brand new word for you guys, brand new topic. Essentially, doing a logarithm is the inverse of doing an exponential. Okay, so just like add and subtractor opposites, multiply and divider opposites, square root opposites, the opposite of an exponential function is a logarithmic function. They're inverses of each other, cancel each other out. Okay, so let's look at one right here and make more sense. So this says, we read this first one right here, part A. We read that log base 2 of 32. That's how you say it, log base 2 of 32. The little number is your log base. All right, so really what that's asking, the way you can kind of think about it in your head, is what would I raise the number 2 to, what exponent would I put on that 2 to make it equal 32? So what would that x have to be? What would I be raising 2 to make it into 32? All right, so you can just count, 2 times 2 times 2 times 2, and it's going to be 5. Okay, so the log base 2 of 32 equals 5. All right, so again, it's just whatever the log base is, you're thinking, what do I raise that number to give me the other number that I'm taking the log base up? Okay, so log base 3 of 1. What would I raise 3 to give me 1? Well, we know that anything raised to 0 is 1. So log base 3 of 1 would be 0. 3 raised to the 0 power is 1. Right? Anything raised to 0 is 1. Okay, now this next one's a little trickier. So notice in this one, the number got smaller, right? So the number gets smaller, it goes from 4 to 2, right here it went from 3 to 1. So in this one, it got bigger. So when it gets bigger, you know that your number is a positive whole number, right, like 5. Whenever it gets smaller, then, of course, if it changes to a 1, you know that it's going to be 0. Log base 12 of 1 would be 0. Log base 1,000 of 1 would be 0. Because anything raised to 0 gives you 1. So when it shrinks, you know you got a special situation. Okay, so on this one, it went from 4 to 2. So you could have a situation now where either your exponent is a fraction or a negative number. So what would I raise 4 to give me 2? Well, we know that the square root of 4 is 2, right? And hopefully you learned this in Algebra 2. If you didn't, then you need to know this, that when you raise something to a half, okay, that's the same thing as taking a square root. All right, the number in the denominator, you treat it like your root. So if that's a 3, it would be a cube root. If that bottom number in your exponent fraction is a 4, it would be a 4th root. So it's a 2, so that means it's a square root. And then the top number right here, the 1, would be the exponent you're raising it to. So that's really like the same thing as 4 to the first, but taking the square root of it. All right. Another one, just to kind of throw another one out there, if you had like 6 raised to the 2/3, well, that would be like 6 squared, but the cube root of it. Okay, so the bottom number is your root, the top number is the exponent. So knowing that, we can determine what log base 4 of 2 is, because we know that 4 to the 1/2 is the same as taking the square root of 4. So the square root of 4 is, of course, 2. So then that means that log base 4 of 2 equals a half. All right, so just to kind of help you think through those, when it's smaller, when the number gets smaller, look for it to be a fraction or a negative number. This next one, you can see that it got smaller, went from 10 to 1 over 100. Okay, so in a situation like this where it gets smaller, but it also becomes a fraction, that's when you need to look for negatives. So what would I raise 10 to make it 1 over 100? Well, we know if we have a negative exponent, then it moves everything to the bottom of a fraction. So what would I have to do? What would I have to have on the exponent to make 10 into 100? Well, 10 squared is 100, right? So if I have 10 squared on the bottom, that would be like raising it to a -2, right? So 10 to the -2 is what would give me this right here. All right, so that's the 1 over 100. So then obviously x, or log base 10 of 1 over 100 would equal -2. Because I've got to raise 10 right here. I've got to raise it to -2, and that'll bring it to the bottom of a fraction, and that'll make it 1 over 100. All right, so those are some kind of basic logarithm examples that you will see. I'm going to let you guys try some of these. Try doing them in your head, and I'll show you how to do them on the calculator, okay, which you'll much prefer, but it's good to be able to understand how the logarithms work. So see if you can figure all these out without the use of a calculator. A part, you should get 4. 3 to the 4th is 81. For B, you should get 0. 25 raised to the 0 would be 1. And for C part, 64 raised to what gives you 8? Well, the square root of 64 is 8, so you got to raise it to a fraction, a half, to make it turn into an 8. And then D part, 2 raised to what gives you 1/8? Well, you're changing 2 into a fraction, which means you need to raise it to a negative exponent to put it on the bottom. And we need to make 2 into an 8 that's on the bottom, so we got to raise 2 to the 3rd to turn it into an 8. So that means we need to really do log base 2. For the log base 2 of 1/8, we need -3. That gives us -3. Okay, so now I'm doing this on the calculator. There's a button on the calculator that you can use to do log bases. Okay, especially if it's one that doesn't work out evenly. You know, like if this said log base 3 of 80 instead of 81. Well, 3 doesn't raise to anything as a whole number to give you 80. So if you get ones like that, then you can use this button on the calculator. Of course, you can always do these in your head. Okay, that's why I showed you these. So hopefully if you see some of them like this, you can do them real quick in your head instead of having to type them into the calculator. It's always good if you can do things quicker. So when you see ones like this, you can do those quick. But if you aren't sure of yourself and want to make sure you're positive, you can always use the log base button on the calculator. So go to math, and then you scroll down or up. Up's quicker to scroll. If you scroll up, it'll be quicker to log base. And then it just gives you the blanks to put everything into. So I can do log base 3 of 81 and hit enter, and it'll spit out 4. I can do log base. What was the other one? Log base 2 of 1/8, and it'll spit out -3. So it'll do these for you, which is nice. Just be aware that you can do them quick in your head if you want, or you can use the calculator. But got to understand how log bases work. It's really just asking you to find the exponent, right? The important thing is you're finding the exponent that you would raise the log base to give you that number. That's really what a logarithm is. Okay, so let's look at some other properties of logarithms. So this first one just says what we talked about in the last stuff. Log base A of 1, I mean, if A is anything, log base of anything of 1, log base anything of 1 is always 0, because anything raised to 0 will give you the 1. Okay, then this one right here is saying log base anything of that same thing will equal 1, because you're asking, what do I raise A to get A? Well, you raise something to the first to get itself, right? So log base something of itself is always going to be 1. Right here, if you have log base anything of itself raised to an exponent, then that's just going to give you that exponent. Okay, so essentially what happens here is you got the two operations that cancel each other out. Log base A cancels with base A, right? Right here, A is the base of this exponential. We've got A to the x. So when you've got a base A, a log base A of a base A, right? Log base A, and right here you've got a base A. Those cancel out, and it just leaves the x. Okay. Similarly over here, same thing, just the other way around. You've got a base of A raised to the log base of A. So that situation is another situation where they just cancel out. Base A and log base A cancel, and it just leaves what's left, x. Okay, so those are situations when you've got to use those properties. If you've got the same base and the same log base, they just cancel each other out. Okay, so if you're doing the log base A of a base A, or you've got a base A raised to a log base A, they'll cancel. So let's practice those real quick a little bit. So this first one, it says log base 4 of 4 equals x. So let's figure out what x is. Well, 4 raised to what will give me 4? Well, we know that's 1, so x is going to equal 1. Okay, it's pretty simple. Right here we've got a log base 5 with a base 5. We said those are going to cancel, right? So those cancel out and just leaves x. Right here we got a base 7 raised to log base 7 of 14. So a base 7 raised to log base 7, it cancels, and it just leaves 14. Yeah, and that 14 is not in the exponent. Over here, the x, they're not in the exponents anymore. They're just, you know, regular bases now, okay? So they're not an exponent. They're just there as the answer, okay? So then this last one, log base 2 of x equals log base 2 of 3. Well, notice these are both log base 2 of something. So whatever you're taking, if they're equal, then the two things you're taking the log base 2 of have to be equal because you're doing the same thing to both sides. So that means x has to equal 3. Okay, that's just kind of common sense. If you do something to one side and you're doing it to the other, then those two things got to be equal. All right, so I want to pause it, let you guys try these down here, see if you can use the properties of logarithms. On the first one, you've got a base 3 raised to a log base 3 of 2x. So the base 3 and log base 3 cancel out and just leaves 2x. Okay, no way to solve for x right here because you don't have an equation, so you just have to leave it as 2x. B part, log base 8 of 8. Well, those two essentially cancel out and just leave 1 because they're opposites of each other. You can think of, you've got a base 8 raised to the first, or you can just think, you know, you got 8 raised to what will give you 8. 8 raised to the first will give you 8. Okay, so in C part, log base 12 of a base 12 raised to 5x. So log base 12 and base 12 cancel and just leaves 5x. And then D part, log base 5 of 2 equals log base 5 of x. So you're taking log base 5 of two different things and they're set equal. So then those two things got to be equal. So 2 must equal x since I'm doing the log base 5 of the same things. All right, so that's properties of logarithms. Now let's talk about two special kinds of logarithms. All right, so your bases can be anything. You do a log base 5, you can do a log base 12, you can do a log base 30. Okay, those can be anything. But there's two special kinds that happen a lot of times in the natural world and in real life. One is called the common logarithm. So the common logarithm is if you have a log base 10. Okay, log base 10, we call it common logarithm. And it's so common that we don't even really use the base 10 when we have a log base 10. If you just see it say log, then that means it's a log base 10, okay? Because it's just the common one that we use. So if you don't ever see a base down here, you can understand that if there's something missing right here, then it must be 10, okay? So if it's an empty space under your logarithm, there's no base, it's automatically 10. It's understood. All right, so a common logarithm is just log. Natural logarithm is if you have a log base e. We talked about e in the last section. So log base e is called the natural logarithm. All right, and you'll see instead of log base e, you'll see ln a lot of times. Okay, and most of the time. Don't ask me why it's ln instead of nl. I don't know. It would make more sense for it to be nl instead of ln, but they use ln for the natural logarithm. Okay, so anytime you see ln, you can just think log base e. Anytime you see just log, think log base 10. Okay, so let's use our knowledge now of natural logarithms and common logarithms to solve some more logarithm problems. So we got ln of 1 over e. Okay, well ln, when we see that, let's think log base e. So we got log base e of 1 over e. So what would we raise e to get 1 over e? Well, remember, since it moved to the bottom of a fraction, we're thinking we must have raised it to a negative. So e would have to be raised to some negative amount to get 1 over e. Well, what would it be? Well, if I move it to the bottom, it'll make it positive, and I don't have any other exponent on e, so it must just be e to the first. So then ln of 1 over e is negative 1. If I raise e to the negative first, it'll give me 1 over e. Okay, B part, I got log base 10, right? It's a common log of 100. So that's really log base 10 of 100. What would I raise 10 to get 100? Well, 2, right? So that equals 2. Okay, next one, I got 2 ln of e. So 2 and ln is really, remember, log base e of e. So what would I raise e to get e? Well, obviously that's 1. So it's really 2 times 1, which is 2. All right, there's your answer for C. And then D part, 5 times log base 10 of 1. Right, what would I raise 10 to get 1? Well, we said already, anything, the log of anything to get 1 is 0. So the log base 10 of 1 is 0. 5 times 0 is 0. All right, so those are some examples of common log, natural logs. Try these other ones down here, and let me know if you have questions. I'll come around and help. First one, 5 times the log of 1,000. So it's really 5 times log base 10 of 1,000. And we are thinking 10 raised to what gives me 1,000? Well, 10 to the third is 1,000. So log base 10 of 1,000 is just 3. So you got 5 times 3, which is 15. B, you take the log base e of e to the third. Well, you got log base e of a base e. So those cancel out and just leave 3. And in C part, you got 3 times log base 10 of 10. Well, the log base 10 of 10 is 1, because the log base something of itself is just 1. So you got 3 times 1, which is 3. And in D part, 4 times the log base e of 1. Well, again, any log base of 1 is going to be 0. So log base e of 1 is 0. 4 times 0 is 0. So let's look at graphing logarithmic functions. This is the last thing we'll talk about. So right here, you can see this graph is the exponential, right? This is the exponential functions that we talked about yesterday. So you have a 2 raised to the x. Your exponent is a variable. That's when it's an exponential function, anytime your variable is up in the exponent. So that's an exponential. Here's the same logarithm function. So this is log base 2, right? So right here, you've got a base 2. Right here, you've got a log base 2. Those are inverse operations of each other. And we talked about how functions that are inverses of each other, when you graph them, right, they mirror across the line y equals x, right? So you've got this line through here, y equals x. Notice how those graphs mirror across that line. So that happens anytime that you've got two functions that are inverses of each other. And this is a situation where these two are inverses. Base 2 of x and log base 2 of x are inverses. So what that means is, you know how on exponentials we had an asymptote right here? We had a horizontal asymptote. Well, now our asymptote for logarithms is a vertical asymptote. Okay? So vertical asymptote at x equals 0, which is going to change our domain of the function. Okay? For exponentials, the domain's all real numbers. The range, would be anything bigger than 0. But for logarithms, it's the exact opposite. Remember, they're going to swap places. So now your domain is when x is bigger than 0, and your range is all real numbers. Okay, so let's look at some other specific graphs. Most of these are just shifts. Okay, so right here, you've got log base 2 of x, and then the plus 3, right? We're not taking the log base 2 of the 3, we're just taking log base 2 of x. So the plus 3 is on the outside. Well, we know when we add or subtract something on the outside, it takes our function and it just shifts it up 3. So we're essentially going to have this logarithm function we had over here, log base 2 of x, because it's still log base 2 of x, but we're going to shift that function up 3 units. Okay, so we can pick out some points right here if we want. Right here's a point at 1, 0. We've got a point at 2, 1, at 4, 2, right, and at 8, 3. And we can just shift all those points up 3 units. Okay, so we're going to go over 1 and up 3, and over 2 and up 4, right, and over 4 and up 5, and over 8 and up 6. All right, so we can see this function now is going to do this, and it's still going to have the asymptote at 0. Okay, the asymptote doesn't move because all we did was shift it up, right? We didn't shift it left or right. So that would be the function for log base 2 of x plus 3. All right, now this next one, you're subtracting one on the inside, right? It's on the inside of the parentheses. That we know that moves it left and right. So the minus 1 is going to move it to the right, which means our asymptote now is going to be right here. And our points are still going to be really located in the same spots as these, just moved over 1 point to the right. So I'm going to move this point over 1, this point over 1, this point over 1, this point over 1. It's going to move them all to the right 1 unit. So now I've got a point here, one here, one here, and then the other one is out here somewhere, right there. Okay, so the exact same shape of the function, just move to the right 1 unit. Okay, so that's how you do these. I mean, we know how to shift functions, you know, vertically, horizontally. You know how to flip them, right? So if you had to flip them across the y-axis or the x-axis, we know how to do that. So you guys try these last couple right here, well, let's take the domain first before we move on. Put those in interval notation. That's part of our graph. So right here, our domain is going to be from 0 to infinity. And we use parentheses on 0 because we will never ever touch 0. So it'll be from 0 to infinity. On this one, it would be from positive 1 to infinity. So that's the domain for that. All right, you guys try the domains for the next two and graph in the next two, and then I'll talk about it. On this first graph, you're just going to shift everything left 3 points. So your domain goes from -3 to infinity. On the second graph, you're taking the log base 2 of -x. And notice that that negative is on the inside, right? So that's on the inside. You're taking the log base 2 of the negative. So that means you're going to flip the function across the y-axis. If there was a negative on the outside, then that would flip it vertically over the x-axis. So we're just going to reflect all of those points that were in our regular function. Okay, they're just going to be reflected over the y-axis. So 1, 0 is going to become -1, 0. 2, 1 is going to become -2, 1, and so on and so on. So that's where we get these points right here. We got one there, 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 and there, because those are the ones that we reflected. And if you're wondering where we got those points to begin with, of course we got them from the graph where we could see that they were crossing. But if you think about, if you plug those values in for x, okay, if I plug 1 in for x, 1 in for x, log base 2 of 1. Well, 2 to the 1 is 0. Anything log base anything of 1 is 0. So I know it's going to be the 0.10. Plug in 2, log base 2 of 2. Well, 2 to the what is 2? 2 to the first. So that's why we got 2, 1. Plug in 4 for x, log base 2 of 4. 2 squared is 4. So you go over 4 up 2. Plug in 8, log base 2 of 8. What I raise 2 to get 8? 3. So go over 8 and up 3. Okay, so that's where those points are coming from. I'm just plugging all those x coordinates in right here for x and doing the log base 2 of those, and that's giving me the y coordinates for those points. All right, let me know if you have any questions on any of this stuff. I know that logarithms might be completely new and confusing. If they are, you know, just let me know. I'll come around and help you out. Those are the practice problems. If you want to practice, if you need help, let me know. Appreciate your all's attention.